In this video, we're examining the role that differential temperature advection plays in the modification of the lapse rate, and this is term C from the lapse rate equation, du dz dotted with the horizontal gradient of temperature. Vertical wind shear changes the lapse rate because temperature advection varies with height. Consider the example shown below. The temperature gradient points from left to right and so is positive. In the low levels we have warm air advection, and the upper levels we have cool air advection. So what's going to happen to the lapse rate and the stability? Well, du dz is negative because we move from a westerly to an easterly, and del h of t is positive, so the whole term is negative. That means that the temperature with height will decrease over time, and so this represents an increasing lapse rate, because remember gamma is minus the t dz, and because we increase the lapse rate, we have cold air advection over warm air advection. We're decreasing the stability, making the layer more unstable over time. So let's look at this in a little bit more detail, this term du dz dot grad h of t. We can write an equation for the vertical wind shear of the geostrophic wind, remembering that the geostrophic wind is the balanced wind where there's a force balance between the pressure gradient force and the Coriolis force. This wind shear is known as the thermal wind. It's not actually a physical wind, but simply a statement of the wind shear, and it's referred to as the thermal wind because it's related to temperature gradients. If we consider a thin layer of atmosphere, du g dz is equal to g on f t bar, where t bar is the mean temperature of that layer, k cross grad h of t, the horizontal temperature gradients. That's illustrated graphically in the figure below, where the mean isotherms are running from northwest to southeast, and so the gradient of the horizontal temperature field is pointing to the northeast. Because F is negative in the southern hemisphere, this means that the thermal wind, the wind shear of the geostrophic wind, runs parallel to the isotherms with the cold air on the right. So let's consider what happens in the real atmosphere with geostrophic winds and temperature advection. So we're looking on whether or not the geostrophic wind will perform differential temperature advection and modify the lapse rate. So for this setup with east to west running mean isotherms and a temperature gradient that points towards the north, in the southern hemisphere the thermal wind, that is the wind shear of the geostrophic wind, will be a westerly. That's u subscript t, or du g dz. Here's the geostrophic wind at the bottom of the layer, and here's the geostrophic wind at the top of the layer. And you can see that if you add the thermal wind, the geostrophic wind shear, to the low level wind ug1, you obtain ug2. Now let's look at the components of the geostrophic wind at the bottom and the top of the layer that run perpendicular to the mean isotherms, because that's the component that's going to perform temperature advection. At the bottom of the layer, that's the component of the wind that runs perpendicular to the mean isotherms, and at the top of the layer, that's the component that runs perpendicular to the mean isotherms. And you can see that they're exactly the same. Why? Because the wind shear of the geostrophic wind with height runs parallel to the mean isotherms. There is no component of it that runs perpendicular, and therefore there will be no change in the thermal advection performed by a geostrophic wind with height. In other words, the geostrophic wind performs no differential temperature advection. All it can do is advect whole layers and replace one lapse rate with another. It can't perform differential temperature advection and modify the lapse rate locally. But the geostrophic wind does not represent the entire horizontal wind. We can decompose the horizontal wind, UH, into a geostrophically balanced component, remembering that's the component of the wind where there's a balance between the pressure gradient force and the Coriolis force, and the remainder, which is the ageostrophic wind, or the non-geostrophically balanced wind. We can then take term C and decompose the horizontal wind into these two components, the ug dz dot grad h of t and the uag dz dot grad h of t. When we write the ug dz in terms of the thermal wind, there's an expression that's k cross grad h of t dot grad h of t, And I'll leave it to you as an exercise to show that that's equal to 0. So what we're left over with is that it's only the ageostrophic wind component that does differential temperature advection. Let's look at that schematically now. So here we have a layer similar to before, and we can show the geostrophic winds at the bottom and the top of the layer, and then the total wind. So the total horizontal wind at the bottom of the layer is U1, and at the top of the layer it's U2. Again, the thermal wind runs parallel to the mean isotherms. You can see now that there is a shear vector, a wind shear vector, between the total horizontal wind at the bottom and top of the layer that is not parallel to the mean isotherm. And this shows that there is going to be a differential temperature advection. So in this particular example, U1 has a stronger component perpendicular to the mean isotherms, and so there is strong cold air advection at the bottom of the layer. U2 has a weaker component of wind perpendicular to the mean isotherms, so there is weaker cold air advection. So in this case, the bottom of the layer cools faster than the top of the layer, and this results in stabilizing the layer. The shear vector is pointing from warm temperatures to cold temperatures, and that's indicating that the top of the layer is warming compared to the bottom of the layer. So the actual wind shear vector in this case points towards cooler temperatures, and when the wind shear vector points from warm to cool for a layer, that means that the layer is stabilizing. And that's what's said here. If the actual shear vector for a layer is directed towards lower mean temperatures for a layer, or thickness, the top of the layer is warming relative to the bottom layer and the layer stabilizes. If the actual wind shear vector for a layer points towards higher mean temperatures, or thickness for a layer, the top of the layer cools relative to the bottom of the layer and it destabilizes. What's shown in this figure in the solid lines is the 1000 to 500 hectopascal thickness, and that's simply the depth between the 1000 hectopascal surface and the 500 hectopascal surface. This thickness pattern, as we'll see later, is related to the temperature distribution. Shown here also are the winds, the mean winds in the layer 1000 to 500 hectopascals, representing the shear between the top and the bottom of the layer. So in region A, you can see that the wind blows from high values of thickness, or warm conditions, higher temperatures, to cooler values of the thickness, or cooler temperatures. So in that region, there's stabilization, advection, differential advection producing stabilization. Whereas in area B, the wind's blowing from lower temperatures to higher temperatures, or lower thickness to higher thickness, and so we see destabilization. Another way of looking at this is to look at some model fields. So here we have from an old numerical model known as Lapse the 500 hectopascal temperatures at analysis time, and then an 18-hour prog field, or prognosis field, on the right hand side. And then the field beneath is the analysis minus 18 hours. So the dashed regions show that there's cooling over the 18-hour period, and the solid contours show that there's warming over the 18-hour period. So where will the atmosphere stabilize and where will it destabilize? If you've said where the atmosphere is cooling aloft, then you'd be correct. So very often we examine the 500 hectopascal temperature field to see where the atmosphere is destabilizing, looking for upper level cooling over time, which will tilt the lapse rate.